This is lesson 2 of college algebra. We are beginning our discussion on the introduction of sets and real numbers and set theory. Today, in a particular way, we are going to define the sets of real numbers and classify values in terms of those sets. So our objective is to define the sets of real numbers and also classify values. The real numbers consist of the following sets of numbers. There are irrational numbers. These are non-terminating, non-repeating decimals. So for example, pi, that's a pretty common one everybody knows and has that as an irrational number on the tip of their tongue, but some that you might not consider is the square root of any number that is not square rootable. So the square root of 2, the square root of 5, etc. All of these are irrational numbers because if you were to calculate them, you would get a non-terminating, non-repeating decimal. Terminating and repeating decimals are rational numbers. Under rational numbers are included integers, whole numbers, and natural numbers. Okay, we're going to break this down. Let's organize real numbers. All right. So a natural number is indicated usually by a letter N. This is the set of counting numbers starting with 1. So the set, usually a set is indicated by these braces or little squiggly lines. Begins with 1 and goes to 2, 3, 4, and we're going to say ... because it goes to infinity. Whole numbers are usually indicated by the letter W. These are all natural numbers. Plus 0. So we start with in the set with 0, 1, 2, 3, and again all the counting numbers to infinity. For some reason, integers is indicated by the letter Z. I do not know why, but it's not I. Irrational numbers is indicated by I. The integers are whole numbers and their opposites. So this includes all of the negative counting numbers. So we're just going to say ... We'll start with -3, even though it goes -4, -5, -6, etc., down to negative infinity, -2, -1, 0, 1, 2, 3, all the way to positive infinity, but only counting those counting numbers, those that would fall directly on a tick line on the number line. Rational numbers are indicated by Q, because they can be written as a quotient. A rational number is any number that can be written as a fraction. Okay, so that includes all terminating and repeating decimals. And then finally, irrational numbers, which are included in the set of real numbers, is indicated by the letter I. This is any number that cannot be written as a fraction. So this is all non-terminating, non-repeating decimals. If you look at the little graphic over here on the left, you would say the innermost circle is all the natural numbers. All the whole numbers includes all the natural numbers, which is why the natural numbers is inside the whole numbers. The only thing added is the number 0. The next bubble out would be the integers. This includes all whole numbers and natural numbers, which is why they are concentric circles inside. And then rational numbers includes all integers, whole numbers, and natural numbers. Real numbers includes all rational numbers, integers, whole numbers, and natural numbers. And then off by itself, but still part of the real number system, are irrational numbers. Okay? Take a moment, go ahead and pause this video to classify each of these numbers as belonging to any of the sets. Again, recall, if the number is a natural number, then it's necessarily going to be also a whole number, integer, rational number, and real number. If the number is an integer, it will also necessarily be a rational number and a real number. So for example, number 10 is an integer, so it's also a rational number and a real number. Okay, go ahead and take a moment, pause this video, and complete the sets.
Yeah, we have plan A's.
Okay, take a moment to check the work here. The square root of 30 is irrational and real. Pi is irrational and real. 24 over 8 is equal to 3, so this is actually a whole number. It's also a natural number, a whole number, rational, integer, rational, and real. 2.48 is rational and real. The square root of 5 is irrational and real. The square root of 81 is 9, and we got a negative in front of it, so negative 9 is integer, rational, and real. For number 8, this is a fraction, so this is rational and real. And then for number 9, pi minus pi is equal to 0, so that's whole, integer, rational, and real. Okay, let's just take a moment to also discuss a little bit about set notation. Okay, we're going to write in several, we're going to write sets in several different ways. Okay. Again, a set is simply a grouping of numbers. So the sets of natural numbers, whole numbers, integers, rational numbers, and irrational numbers, as well as real numbers, these we call universal sets. But a set of numbers can be any grouping of numbers. When we talk about the elements of a set, an element is said to be, we call that element an X. We say if X is a member or an element of S, the notation for this is to write it as X is an element of S, where X is the element and S is the set. If X is not an element of the set S, then we write X element. It looks kind of like a curvy E, but if it's not an element, we put a slash through it, and a set of S. So again, S is considered the set, whether it's a universal set or some given set that we have, and then X is the element, or in this case, not the element, as the case may be. All right, let's talk a little bit about set notation. Set notation is a way to write a set. Okay, if we have just a straight up set, we're going to list the elements between the braces. Okay, so we have a brace, we have, let's say, our elements for our set are 1, 2, 3, 4, 5. Okay, so we simply list out the given elements in a set. All right, so that would be just a list notation or set notation. Okay, interval notation. This can only be used for a range of numbers. And usually it's indicative of real numbers. So let's say, for example, I have a graph. Let's say it's a parabola, something like this. Okay, and I ask, let's say the vertex of the parabola lands on 1, 1, and I ask, what is the range for this set? Okay, so this would include every single real number between 1 and infinity. So the range would be 1 to positive infinity. The bracket indicates that 1 is, included. Okay, and you always use parentheses to indicate infinity. You also use parentheses if the number is not included in the set. Set builder notation specifies the certain attributes of the set. Okay, students usually struggle the most with the set builder notation, but it isn't actually that hard as long as you figure out how to decode the symbols. So if we say the set of S is equal to X, we're going to let X be all the elements such that 1 is less than or equal to X is less than or equal to 5, and X is an element of the integers. What we have just described here is this set right here, 1, 2, 3, 4, 5, but we've done it in set builder notation. So what do these smaller pieces of set builder notation mean? Okay, well, let me get something else to write with here. So S, of course, is the set. These are all the elements, and now I'm going to describe the elements. Okay, this bar right here means such that. And then I use inequalities to describe the fact that I want all of the elements to be between 1 and 5 inclusive. So this is the interval for the elements of the set, including 1 and 5. And then finally, I want to say that all of the elements are integers. So I'm indicating to what universal set all of the elements of the set belong. Or I could just use verbal notation. So this is plain language. So I could say, all right, let's talk about this set right here. This is the set of all integers between 1 and 5, but I'm including 1 and 5, so I would say inclusive. Okay, let's take a moment to practice with set notation here. So again, interval notation, this is only for all real numbers. Okay, so you can't really use that for integers and such like that. So we'll go ahead and cross these out. Okay, again, this is the set. It looks like I start with -5, but I'm going to negative infinity, so I got -5, 0, and 5. So this ... is indicating that I've got a set that actually continues, but because I can't sit here and write numbers for an infinite amount of time, then I need to put some ellipses here in order to indicate that the set goes actually to negative infinity and then also to positive infinity. If I were to write this using set builder notation, I would say, okay, this is the set of all elements x such that x is equal, well, I want the multiples of 5. So I need to multiply 5 by some number n, where n is an element of the integers. So that tells me all of the parts of this set. It gives me all of the attributes which are included in this listed numbers here. Or I could just use verbal notation. I could say I want all the integers that are multiples of 5. Okay, and then that would work. Let's take a look at number 2. I'm seeing that this set is written already in set builder notation. It says the set is equal to all elements x such that these elements x are equal to 2n, so I'm taking integers because n is an element of the integers, and I'm multiplying them by 2. So in other words, I want all the integers that are multiples of 2. In other words, so I would start ... This would be -4, -2, 0, 2, 4, ... Another way of saying the multiples of 2 are all the even numbers. So that would be my straight up verbal notation. For number 3, I've got some interval notation here. And it shows me that I want all of the real numbers that go from negative infinity to 4, but I'm not including 4. Okay? I actually can't write this as a list of numbers because it would be impossible to write every single real number because they're not counting numbers. There's an infinite number of numbers between 1 and 2. Okay, so I can't actually list it in a list way, but I can use set builder notation. I could say I want the set of S, and it doesn't matter really what letter you choose, it's just the word set starts with S, so I'm using S, is equal to the elements x such that x is less than 4 and x is an element of the real numbers. Or I could just say I want all the real numbers less than 4. And I'm not including 4, so I wouldn't say less than or equal to 4. And then finally, for our skills practice, we got an example that reads in verbal notation that we want the set of all integers between -10 and 10 exclusive. So this is including the numbers -9, -8, -7, -6, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I indicated ellipses in the middle to, oops, sorry, not 10. 10 is not included. I put ellipses in the middle to indicate that the pattern continues in the middle there. We can't, again, write this in interval notation, but we can write it in set builder notation. So this is the set of all elements x such that x is an element of integers. You see it doesn't actually really matter what order I put it in as long as I get all the attributes in. And then I want -10 to be less than all of the elements x less than 10. All right, so this is kind of an introduction to how to write a set when we're given particular sets. It is actually very important that we know the universal sets, but also that we have a good understanding of how to write sets. So next time we are going to discuss various other kinds of sets, such as null set and what a subset is, and then we're going to perform some operations on sets. So until next time.